Ising model with interactions J1 and J2 in the horizontal and vertical directions. So the axis labeling along the rows, I go I, along the vertical, I go J. And the coupling is J1 between Si and Si plus 1, and J2 when it is I J plus 1. So that is the energy expression, and my goal is to calculate the partition function, which is e to the power minus beta E sum over all configurations. And therefore, this becomes sum over all configurations, and it's like beta J1 summation Sij Si plus 1j plus beta J2 E summation Sij Sij. So that's what, and we essentially wrote this without the, wrote this as the J1, we were the beta. So that's what we, and the point was that I want to go from a J row, which is J, to a row which is J plus 1. And so I imagine that the problem has been solved up to row J, and then I go to J plus 1, and that is the part which we were focusing on. So there is this part from J to J plus 1, and which is the analog of the transfer matrix, which we did for the one-dimensional case. That is, go up to do this partition function up to this point, add another spin, and then include that in the game. So then that is where what we were doing, and once again to sort of recall a bit what we had done. This is we focus on these two rows. So it is J and J plus 1. So there is summation I S I S J. Sorry, Sij and Si plus 1j, and then there is the part, so this is with J1, right, that is the J1 I plus 1, and there is a J2. So this is going, I mean, a sum over I, so along the at the jth level, and then the same thing, and then it is the J. I would also have over here Si, and then I have to consider Sij plus 1, and then it is Si plus 1 J plus 1, right? And so that is the J focusing on what is at the jth level, and then what is at the J plus 1th level. So this is it, that sum over I with I plus 1, and with the J held at this J, and then at this sum over I once again, and with the J held at the next J. So this is the part which takes, and what we decided to do was write this as Sj, so e to the power, and we decided to go with this notation that Si on the ith row, Sij is equal to Si, and on the jth row, on the j plus 1th row, Si j plus 1 is sigma I, right? So that's the thing. And we wrote the part of this, which is I plus 1j, and I to I plus 1j, and pick up the I plus 1, j plus 1, and wrote it as Sij j plus 1 minus Sij squared with a half. So that brings up, so you pick up the Sij plus 1, and that's the Si. What happened here? The j to j plus 1, this was sorry, this is Ij, and this should have been Sij plus 1, right? Yeah. So I plus 1 on a fixed j, j, yeah, absolutely. So this part over here, which is the part which is Sij times Sij plus 1. So this is with the j2 over here. So this minus j2 over 2 takes care of that. And you have the other part over here, which is j1. And then it is summation Sij Si plus 1 j. And you also have the, if I'm focused, you have Sij plus 1, Si plus 1, j plus 1. That is the whole story and about the part from j to j plus 1. There is this bit, and what I have, this one was written like this. There were constants which one can drop. And then this is just written with the, that there are this I sums on both of them. So focusing on only on this part, this is it. And then we noted that all the energetics of this part is determined entirely by the number of spin flips. So it is going from j to j plus 1, the e to the power beta, e to the power j1 this and this, which in going from the level j to the level j plus 1, e to the power, this is what we get, e to the power this part over here. And it is easiest to describe it through this flip. You call Si at j spin S3 and Si at j plus 1 sigma 3. And then this part over here is flip minus j2 over 2 S3 minus sigma 3 squared. And over here you have the usual sum j1 this plus the other, right? So everything determined by, so if I write this as e to the power L j to j plus 1. So this is this part over here, all the, and this is summed over. This whole business is going to be summed over Si It is the, and then you write L j to j plus 1, but summation over I is taken into account, and you are just going, this part describes what is happening. Oh, yeah. So this part is simply telling us how to go from j to j plus 1. So j to j plus 1, and then what we find is that if I define spin, the S3 and S3 can be plus 1 and minus 1, and sigma 3 can be plus 1 and minus 1. And in terms of this is what we had reduced it to. So now one can essentially write out this L j to j plus 1 . So going from I have this e to the power L j to j plus 1 describing what is, and this L is given by this expression, the L j to j plus 1 is given by this quantity over here. So that is my L j to j plus 1, and you are e to the power this quantity, which is what? So now you note the following, that this one S3 minus sigma 3, everything, how much this, the cost of going from one step j to other is going to be determined by this spin flip over here. So how many spins are in going from the level j to level j plus 1, how many of them are going to get flipped? So here you are, this is j plus 1 and this is j, and you have these sites, and first the point would be no flip, and the simplest, the lowest energy situation is this no flip over here, and no flip means that it is just 0. So this answer is simply e to the power that part, which is j1 and summation I, whatever else is there. If you have one flip, then I pick up e to the 4 over here. So it is e to the power minus 2j2, and then it is e to the power everything that I had over here. And two flips, so two flips would mean this is e to the power minus 4j2, and then it is all these over here, and n flips would be e to the power minus, it's going to be 2 to the power 2n, right? One flip 2, two flips 4, 2n j2 e to the power. So very good. So if I look at, so what I'm going to do is that if I want to look at what are the, how do I do this sum, then the StatMech sum would be, these are the energetics, then you look for the weighting fraction of each one of them. One flip, there are n, two flips, n into n minus 1 by 2, and you do the StatMech in that fashion. Yeah, sure. So that's the, but that's that we won't do that. We won't be going into actual calculate. We want to show a correspondence over here, which is that this, what is the transfer matrix for this problem? What I'm interested in is finding the transfer matrix for this. That is, what is the Hamiltonian? What we learned from the one-dimensional Ising model is that I could write this step as e to the power minus IH times delta t. That is, the 1D showed us that you could go from this side to the, going from partition function up to this side over here. For that can be written as a step e to the power minus IH delta t, and then you can, all right, you have the correspondence between the one dimension. So it is the correspondence that one I'm interested in at this point, rather than evaluating the partition function. And that correspondence is would have to be what takes you from j to j plus 1. It is, I wanted correspondence where I can write it like e to the power minus IH times delta t here, going from j to j plus 1. So I have written this. So in terms of, so what will H be in terms of? The 1D already told us given that it is a spin up, spin down system, the H in 1D was related to the sigma matrix, the sigma i's, right? It's once again a two-state system, and therefore the relevant things would once again be the sigmas. But in the one-dimensional case, I could do with just one sigma. Over here, I will need a sigma at every point I. Each point over here goes to the next through a sigma. And I have a, and they are coupled because everywhere I have this this term is always there. I coupled with I plus 1. So whatever I do, there is a coupling along this direction. Along this direction, I will move according to, I mean, the Pauli matrix over here. But along the chain, I'm going to, so that is where we stop, that what we are going to have over here for the two-dimensional Ising model is a one-dimensional, a quantum problem on a one-dimensional chain. Over here, it was a quantum problem on just at a point. It was a quantum problem at a point, just a sigma matrix which had to be worried. Over here, it is a quantum problem. It's a many-body quantum problem. Each one of these are sigma, has their own sigma matrix, and they are coupled to the nearest neighbor. So you have a many-body, one-dimensional, many-body quantum problem. So that is the difference. So if you can now imagine that if I went to a three-dimensional Ising model, it would be a coupled problem on a plane and then going from this to this. So there would be the d-1 dimension you would have these coupled problems, and the spatial coupling is in d-1 dimension and the other dimension. So I take a d-dimensional StatMech problem, and the quantum problem that it becomes is coupled in the d-1, the spatial business is going on in d-1 dimension, and the time is the direction in which the transfer matrix propagates. That's the link between, so all right, so what exactly is the going on? So now the last bit is that my goal is to write things like e to the power, which for small h is going to be e. So this is over h bar. So for step one, this step to this step, it has to look like this. So that is so now I look at this no flip situation, and no flip, and the point is that the matrix element over here, I mean, you take the no flip Hamiltonian, and it is whatever, if I call this part, if I have a name for this part over here, call it maybe or some h prime, maybe it is an e to the power, let's say some h0, what or h prime, whatever. Anyway, so it's some h prime, which has to, which is the no flip part of this. When it comes to this, you notice that it is e to the power minus 2j2 times this e to the power h prime. And when it comes to these n flips, it is e to the power minus, so this chap is always there. This e to the power h prime. It's always there, and you are multiplying by. Now, so what is it that we are looking at? It is the question of spin flips. So the thing we are the Hamiltonian that we are trying to look at, because we are, this is flip, there can only be one, I mean, it's a up becoming a down over here, down, or a up becoming, keeping up over here, or a down becoming a up over here. So that is the thing with, so it is a question of being able to flip at this question of one flip or two flips, refer to different sites over here. Yeah, I mean, that is, so the one flip means over here that you have flipped only at one site. Two means that you have flipped at two sites, but at each site, the flipping is going to be determined, flip is determined by the Pauli matrix sigma 1. So sigma 1 is the flip, and what determines the flipping business. So one flip. So one flip over here. So I'm going, the first one, no flip, looks like this. The one flip looks like this. And so what is going to happen is that if you are going to look, the part of the Hamiltonian, that you are going to generate, that part is going to be, this is the part which is going to be associated with this sigma 1 over here. So it is going to be, it is this part which is associated with the sigma 1. Similarly over here, these would be the parts which are determined by the there is sigma 1 at one side, over here sigma 1 at two sides, and so on and so on, so forth. And this part is just the no flip part. And so, all right, now I want the matrix elements. All right, but the matrix elements, I am in the business of trying to figure out what is this Hamiltonian which takes me from J to J plus 1. So when I look at these flips, I know what this Hamiltonian is going to be. The Hamiltonian over there, for the flips, the Hamiltonian, so H for flips has to be the sigma, a sum over sigma I. So you are going to pick up a sum at every site. There has to be a sigma 1I summed over I. So at every site I, there is a sigma 1 sitting, and that is the chap which tells you whether there is going to be a flip or not. Huh? Ida? I is the site index. Yeah. I is the site index. So I is the site index, and the when it is sigma 2 টা হলো না মানে this is going to tell you that it is there is a sigma 1 which, I mean, you can, if you have a sigma 1 now, the different states would be that how many flips. The wave function will be a string of wave functions which are essential at every point in this on this lattice. It will be described by a two-state wave function which is a direct product, right? So there is site 1, 0, 1, or site and then maybe 1, 0, and so on. So at every site over here, I mean, if it is site 1 is 0, 1, and site 2 is so this is the wave function for, I mean, this row over here. For the other row, if there is a flip over here, then the wave function will be 1, 0 at site 1, and the other would be just exactly. So if there is just one flip, that's the wave function over here, right? So it is at every site you have a sigma 1 which is uncoupled with the remainder of the sites. So this is just taking care of the fact that how many spin flips do you have as you go from here to here. So as soon as I write down the many-body wave function for this, there is a sigma 1 at every site. So there would be a wave function like 0, 1 or 1, 0 at every site. And that would be, this is non-interacting, so it is a direct product. Huh? No. This is there can be a flip at every side. So as I said, that if I have a wave function over here in this side, which would be looking like first side maybe it is spin down, second side is spin up, third side this is for this column or this row over here. Go to the next row over here. Every write down the wave function. So that wave function, if there is flip only at one point, will যেখানে 0 1 ছিল সেটা 1 0 হবে কিন্তু অন্যগুলো সমস্ত এক থাকবে। So that tells, it is the wave function which tells you how many flips. The Hamiltonian is simply sigma 1 summed of sigma 1 at side 1, sigma 1 at side 2, sigma 1 at side 3. মানে আমার যদি একটা হ্যামিল্টনিয়ান থাকে which is equal to say split h1x plus h2 x1 h2 which is at x2 side, h3 at x3, তাহলে the wave function is psi x1, psi x2, psi x3 and so on, right? So that's the wave function. So this is x1. I mean, in normally, I mean, it would be like x, y, z. So if you had in the three-dimensional space, x1 as x, y, z, and the Hamiltonian was entirely uncoupled in x, y, and z, then the wave function would be psi x, psi y, psi z. This is exactly what is going on over here, that I have a Hamiltonian, single particle Hamiltonian over here, which is, I mean, a sum over, there is sites. At every site, there is a sigma 1. Right? I mean, I could have a Hamiltonian over here, which is like x1 square plus x2 square plus x3 square. Right? And now over here, you have similarly sigma 1 at site 1 plus sigma 1 at site 2 plus sigma 1 at site 3 and so on. Huh? No flip, the actor site to kono flip at prashno nahi na. It is, this is at site 2. This is on, all of this is on row J. Similarly, at row J plus 1, you have a similar Hamiltonian. And ebare shetar hocche kintu মানে তারও এখানে sigma 1 মানে at site 1 and this, but now it is a question of wave function না, এইখানে wave functionটা can be 1 0 তার আর সবকিছু যা কিছু আছে মানে এটাও can be 1 0, এটা হয়তো 0 1, এটা হয়তো আবার 1 0। আমার যদি একটা স্পিন ফ্লিপ হয় তাহলে এইখানে ওয়েভ ফাংশনটা এইটা বুদ্ধি অন্যগুলো সমস্ত এক থাকবে, রাইট? কার জন্য? প্রত্যেকটা যেতে তো সিগমা 1 আছে। হ্যাঁ কেন ফ্লিপ? হোয়াট ইজ প্রত্যেকটা যে ফ্লিপ হবে? ফ্লিপ তো তখনই হবে যদি এইখানে সিগমা 1টা করেসপন্ডস টু 1 0 আর এই সিগমা 1টা করেসপন্ডস টু 0 1। ফ্লিপ তো ইজ অনলি বিটুইন যে এই রো আর এই রো। আপনার এরকম হয় 0 1 আপনার 1 0 তো আপনি যদি একটা 1 0 স্পিড অ্যাড করেন তো সেটা হয়ে যায় 0 1, তো মানে ফ্লিপটা চেঞ্জ হয়ে যায়, তাই না না কিন্তু সেটা তো এক করাবার কোনো মানে why should you মানে what you have to describe is that there is a system zeta sigma. It has a sigma 1 as a Hamiltonian, and it is but it's a many body Hamiltonian. There is a sigma 1 at every site. There is a sigma 1 at every site. This sigma 1 is capable of a spin flip. Kintu eikhaneo there is a sigma 1, eikhaner je Hamiltonian ta, it is a spin half system or Hamiltonian. There is a spin half. Imagine there is a spin half lattice in one-dimensional lattice over here, and there is a spin half one-dimensional lattice over here. A spin ta ami flip koracchi na. I'm not interested in knowing whether this spin has flipped or not. I'm only interested in knowing whether this spin has flipped or not. You get the point? Mane ekhane kintu amar ei spin ta flip hoyeche ki hoyni seta niye ami I am not introducing sigma 1 so that I can talk about this chap spin. It is a sigma 1 at every site, and I can now look at the, so there is a many body wave function. And ওই many body wave function টায় spin flip হয়েছে কিনা? হ্যাঁ, you see, I have a set of sigma 1s over here, which I write as so site sigma 1 I, which means that this is a sum over I. Sigma 1 is the sigma matrix. Sigma matrix, it is the sigma 1 matrix. Sigma 1 matrix at this site 1, sigma 1 matrix at this site 3, 4, 5. So there is this, which is a sum of all these sigma 1 matrices. I have no external field which can flip or do anything. So, but I have a second row over here. And there is a second row over here. And the point is that this row over, say, call it 1 prime. So in this position, which correspond that label below 1 prime, 2 prime, 3 prime, and so on. And my interest is in the configurations. They are all, if this is up, then this is also up. This is up, this is also up. So the wave function, if I write down a wave function of this, which is going to be a wave function which is 1, 0, 1, 0, 1, 0 at every site, all of them up. Tale if there is no flip, tale eitaro prottekta hobe 1, 0, 1, 0. So it would be the direct product of all these 1 zeros. Ekhane hoche direct product of all the 1 zeros here. So these column vector gulor direct product hoche ei wave function ta. Column vector once again sheta eikhane কতগুলো spin flip হয়েছে, I look at this wave function and find out যে এখানে যদি সব 1 0 থেকে থাকে ওখানে কটা 0 1 হচ্ছে, বুঝলে না? Yeah. It's all non-interacting. So what kind of what is this Hamiltonian? Now I have a magnetic field in the x direction, and it has coupled to the magnetic field. So it is a magnetic moment sitting in, it is a set of magnetic moments sitting in a magnetic field which is in the x direction. Get it? So it is not a question of one magnetic moment in an x direction and we talking about whether that spin can flip by a perturbation or not. When there is no perturbation, nothing. When there is just this Hamiltonian, which is H external vector and dot sigma, and H is in the x direction. It's a many body system because this is summed over all the sites I. H vector tar direction she nije beche niyeche, that's a she x direction. So H, X, I, sigma I, these are site indices. আর যেই H টা বলে দিল সে x direction-এ ও হয়ে গেল H sigma x. So সবাই H sigma x, কিন্তু প্রত্যেকটা এক একটা সাইটে, প্রত্যেকটা সাইটে এক্সটার্নাল ফিল্ডটা সেম, সবাই x direction. This is what the transfer has told you. I have a set of spins along this line over here, and I'm looking at the next line, and I have this partition function which has to take into account, which reduces to studying essentially the configurations in which there is a spin flip. মানে এই পার্টে মানে এই পার্টগুলোর সমস্ত সব এর জন্য এক, it is only this which is different. S belongs to A and sigma belongs to this one, right? So it is S is here, S is, let's say here, sigma is here, and it's S minus sigma, and it is telling you only if there is a difference between these. And the point is that there is a sum over here. It is a S3 at every site. কারণ I এর উপরে sum আছে, এইটা হচ্ছে একটা specific, মানে the I এর উপর sumটা hidden. J plus 1 just এটা লিখছি, কিন্তু I J plus 1 এর মধ্যে তো I এর উপর sumটা hidden আছে. So actually this is S3 at site I and sigma 3 at site I. Okay? So that is what makes it a many body problem. যে আমার পুরো রোটাতে যতগুলো সাইট আছে সকলকে দেখতে হবে। Yeah. So these are the flip strengths, and now all right. So I want to write the whole thing as going from one step to the next step as E, and this is small. This is to be written as IH delta T. So this E from the E to the power, I mean this L which goes from J to J plus 1, this part I want to write as in a as a Hamiltonian time evolution, and it is L j to j plus 1. A j to j plus 1 has become the delta t, and there is a Hamiltonian in the verb which is this. Small delta t is infinitesimal, therefore this is equal to 1 minus I h delta t. There is a h bar divided by h bar. So the matrix elements of this has to match the matrix elements of that. So if there is one flip, then the matrix element of this is this, and if there are two flips, it's this and this. But now the if you have two flips, if you have no flip, then this is operational. No flip is 1 minus IH matrix element, no flip, delta T over H bar. If it is one flip, then this is not operational. Then it is minus IH 1 flip divided by H bar delta T. One cannot have a matrix element between states which has flip. Yeah, it's a diagonal matrix. 0, 1, 0. Yeah, 1 minus 1, 0, 0. So if I have a flip and I'm looking at the matrix element, then it is so if I have n flips, then it has this is this raised to the power n. So you look at the one flip situation, it is like e to the power minus 2j2 times the one flip. Yeah. So there is this part, and then there is a e to the power minus 2j2 times so one flip, two flip in this. Now the point is that so now there has to be one final argument before one can get this done. This, all right. So what about the first one? So this was e to the power j1 times what we had, right? I mean, your no flip, which essentially meant the part of the ji, I mean, all summed over at a fixed j, it is the sum over I, this part over here, no? It is Sij Si plus 1j. That is this part of the Hamiltonian. Okay. So it is the sum over I, which is the part of the Hamiltonian, and if this has this no flip, this is the only chap which can give you the matrix element. So, but this has to look like this, right? The no flip has to look like this, that it is 1 minus this. Only way it can do it if J1 is small. Yes. So the only way this correspondence works is J1 is order of delta T. Right? Now comes so this is H one flip, which is yeah. So this J1, but now comes the one flip matrix element. So this one flip matrix element is like H one flip times delta T. And what does one flip actually mean? One flip means that I have e to the power minus 2j2 extra. Yeah. So this one flip relative to the zero flip is down by a factor of e to the power minus 2j2. So this one flip chap, this e for everything to this one flip chap is of the order e to the power. So one flip is of the order of e to the power minus 2j2. So this is of order e to the power minus 2j2, and obviously the other if I'm going to have the correspondence at this stage that this is H1 flip times delta T, then e to the power minus 2j2 is of order delta T. So e to the power minus 2j2 is going to be small, which means that this J1 e to the power minus 2j2 has to be some constant times J1. So that has to be the consistency. Yeah. So, and if I have any further higher order flips, then in the limit, then this e to the power, now that the next order is e to the power minus 4j_t. So e to the power minus 2j2, I have just argued, is of order delta t, which is small. And therefore, for all other higher orders, it is successively smaller, and therefore the Hamiltonian stops at the identification of the Hamiltonian is completed through a no flip and a one flip. J2 টা see J2 টা হচ্ছে এই one flipper matrix element, মানে one flip matrix element টা is of the order, and এটা তো order unity. So তাহলে one flip matrix element টা is of order e to the power minus 2j2. On the other hand, the one flip matrix element has to be মানে এইটার মানে অর্ডার এইটা, কারণ এইখান থেকেই এই জিনিসটার চেহারা হচ্ছে এর কেবল কন্ট্রিবিউশন আছে ডায়াগোনাল এলিমেন্টে, কিন্তু ওয়ান ফ্লিপে নেই। সো ওয়ান ফ্লিপে মানে এর নেই, ওয়ান ফ্লিপে কেবল এ ক্যান কন্ট্রিবিউট করতে পারে। সো এ কন্ট্রিবিউট করছে ওয়ান ফ্লিপে, এন্ড দেয়ারফর দ্য এই পার্টটা ইজ দিস ইজ H1 flip times delta t. And so it is H1 flip times delta t. From here you argue that the one flip matrix element, no contribution from here, and there is a contribution from here because H has to give the contribution in the one flip zone. But so therefore it is of order delta T. Kintu eidike one flip ta, I know how much energy it cost me to make a flip. It is e to the power minus 2j2. So consistency e to the power minus 2j2 has to be of order j1. And therefore e to the power minus 2j2 has to be of some constant times. Yeah, but the two flips are no longer, I mean, the mapping ignores the two flips because when it delta T square. Yeah. So the mapping from the stat mech to the quantum problem involves only the no flip and the one flip. Oh, J. এই নো ফ্লিপ সিচুয়েশনটা সেইটা মানে এটা হতে হবে যে নো ফ্লিপটা আমার এই হচ্ছে চেহারা, নো ফ্লিপে আমার এই রকম একটা এখান থেকে নন জিরো কন্ট্রিবিউশন আছে, and then there is going to be some H no flip matrix element times delta T. আচ্ছা, এবার নো ফ্লিপে আমার চেহারাটা হচ্ছে e to the power j1 something. যদি j1 টা স্মল না হয় তাহলে আমি এই স্ট্রাকচারটা পাবো না। only if j1 is ordered delta T তবেই আমি এই স্ট্রাকচারটা পেতে পারবো। তাই জন্য j1 টা has to be of order delta T. যখন j1 টা যেই হয়ে গেল order delta T, now you look at the one flip matrix element where এইটা contribute করতে পারবে না, and therefore now you know one flip costs me e to the power minus 2j2, তাহলে সেটা is of order delta T. And therefore and to make things all tie up together is this constraint e to the power minus s. ওখানে তো জাস্ট একটাই, so very good. The corresponding, the stat mech problem corresponding quantum problem is to be written in terms of one flip, zero flip and one flip states, and therefore to be written in terms of Pauli matrices. You see, when the fact that all that I can be interested in the limit of delta T tending to 0, I can ignore the large number of flips, tells me that I can work with a Pauli matrix is a consistent tool. And what is the Hamiltonian then? The Hamiltonian is this part, as we argued, this e to the power where it's just flipping, the just flipping part. See, this part is Just let me get the, where was the Hamiltonian, wherever we started with. It was a J1 and it is a SI J and SI plus 1J, and it was a J2 and going from Sij Sij plus 1, right? All right, that is what we started our with. This is in the line, and therefore it is always there. I mean, that is what it is. When it is no flip, that is the only part that is relevant. And what is that part? That is just sigma. I mean, the S can be up or down, and therefore this is I can write it as the sigma 3, and it is, I could simply write it as sigma 3 at site I and sigma 3 I plus 1. That's when so it is S on I plus 1. Si can be up or si can be down. Sigma 3 is the matrix which is the eigenvalues up and down. So you can write this part without thinking as sigma 3i plus 1. It was this part for which we wanted to have a form. That how does it go from J to J plus 1? So it is this part over here which we were interested in. And for that, we found that it is like a time, it's like it is like a movement in time with this Hamiltonian, and the movement in time is taking place through the fact that along as you move, there can be spin flips. That is, if you start with where the Hamiltonian is decided by this, so you have a spin up here, spin, and so some configuration like this. When I go to this over here, there could have been that this has become this, but everybody else maybe looks the same. But this has changed. So that, to allow for that, what we found that I need to have a sigma 1. And this is at every sigma 1 at every site I. So there is a sum over I here, there is a sum over I here, and you have there is a J1 sitting over here. So there are two different couplings over here, plus this with some coupling strengths this. So if I do take this Hamiltonian over here, then this Hamiltonian describes the process of transferring me from J to J plus 1. Okay. So it is the two-dimensional stat-mech problem has become a one-dimensional quantum problem, but a many-body. The one-dimensionalizing was also a quantum problem, but it was quantum mechanics, a single particle quantum system. Over here, it is no longer a single particle quantum system. I have a many particle quantum system. And they are coupled through the, so what could this, you can make a transformation and write this as, I mean, you can put the, I mean, a 3 goes to 1 and 1 goes to 3. That's a transformation that one can do. So it is common to write this as sigma 3I, so sum over I, and summation sigma 1 I and sigma 1 I plus 1. So you have a set of so written like so from through a unitary transformation, this goes to this, and once you have this, this can have a meaning. So what this means is that I have a quantum Ising model, a one-dimensional chain of quantum spins. That is what this is. It's a one-dimensional quantum problem. So it was a 2D classical Ising, and it has gone to 1D quantum Ising in, there is an external field. Because this, so in the Z direction, there is a transverse, this is in the X direction, these spins. And this is in the Z direction. So there is a transverse magnetic field. So it is a one-dimensional quantum Ising model in a transverse external field. It is Z direction, whereas a coupling gula, a magnetic moment gula or X direction. Good. Uta? Right. So basically এই কোএফিশিয়েন্ট মানে ওই যেটা বললে J2 J1 ছিল এখানে তাদের মধ্যে একটা হচ্ছে ইন্টারঅ্যাকশন বিটুইন স্পিনস এগুলো আর একটা অন্যটা হচ্ছে বাইরের থেকে একটা ম্যাগনেটিক ফিল্ড কারণ এটা তো এই কাপলিংটা ইজ টু আ ম্যাগনেটিক ফিল্ড না এটা একটা সিঙ্গেল স্পিন সো ইট লুকস লাইক আ স্পিন ইন আ ম্যাগনেটিক ফিল্ড identical. This was solved by Feuti in some 1970 something or other, and they're identical. So get the picture. I mean, this is a sort of explicit demonstration that if I have a two-dimensional Ising model, all right, and then there is a quantum problem which equivalent quantum problem in one lower spatial dimension, because the other dimension has to become time. When going from J to J plus 1 is like progressing in time, and the other is still space-like. So, all right, there is still something here which needs What I mean, what is this? And what kind of? Have I got it right? So, two exact answers. Exact. So, exact solution of a two-dimensional Ising model. So, when you may have exact solution 2D Ising. Coupling constant J. So, J S I J S I plus 1J plus J S I J S I J plus 1. So, the isotropic so if this is the Hamiltonian, the critical point is sine hyperbolic square KTC2. No? That's the Onsager solution. Yeah, if it's for the 2D isotropic Ising model with this Hamiltonian over here, the phase transition occurs at a temperature Tc, which is sine hyperbolic square KTC. If it is anisotropic coupling J1, J2, this where in the world is the J? Sorry. Anisotropic, the answer, exact answer is 2J1 by KTC sine hyperbolic 2J2 by KTC. Anisotropic, that's the exact answer. So exact solutions, isotropic Ising is this. Anisotropic Ising with J1 and J2 along the two directions is given by that. All right. I have a relation which I have found a relation which looks like this. So what is this all about? E to the power minus 2J2. So let's look at the limit to J2 over KTC much greater than 1. So J2 over then sine hyperbolic is just E. So then it's going to become sine hyperbolic 2J1 over KTC times E to the power 2J2 over KTC is equal to 1. So sine hyperbolic 2J1 over KTC is very nearly E to the power minus 2J2 over KTC, right? This is, if this is small, because the approximation was that J2 over KTC is much greater than 1. So this is, therefore, this right-hand side has now become small. Left-hand side has to become small. The only way in where it can become small is by 2J1 over KTC much smaller than 1. So need 2J1 by KTC, there should have been a 2 somewhere, over 2, so that is very nearly, I mean it is sine hyperbolic, so it is 2 this, so it is 2. So need this, so it is 2J1, so if this need this to be small, So therefore, this is 2j1 over KTC is very nearly 2e to the power minus 2j2 over KTC. The 2's cancel. So j1 in units of is so j1 is very nearly KTC to J1 in units. Sorry, in units of KTC, J1 is very nearly e to the power minus 2. Right? Get the point? And see the what you have over here. J1 is e to the power minus 2j2. And that says that is the critical bit. So criticality is lambda equal to 1 for criticality. Correct? So now, this is the way the thing unfolds. All right. I mean, for if you had to do this, I mean, find criticality from here, then I would have to find the Hamiltonian has to be diagonalized and the lowest eigenvalue found. And the question is when the lowest and first, between them, the gap is the correlation length, and when that gap goes to 0, that's the transition. So by this mapping does not solve the problem. I mean, you have just recast. What we have done so far is simply recasting the spatial problem of Ising in a quantum in the quantum domain. It still does not tell me what the partition function is, but to answer, I mean, the question which is valid, that I had a relation like this, a consistency relation like this sitting, and what has that got to do with anything? Well, you look at the critical answer. And what this has to do with is exactly the if lambda equal to 1, you have critical. Right. No, nothing is easy. No. One has to understand this is a reformulation for understanding additional features which come. The transition, I mean, the Onsager solution tells you that there is a transition at particular TC in the general form. I mean, that tells you that that is the critical temperature. After a huge amount of work, it is not that the work gets, if you have to get it from here, you have to actually diagonalize this Hamiltonian and look at the spectrum and find the, it is the gap, the ground state and the first excited state gap, which determines the inverse of it, determines the correlation length. And when the gap vanishes, that is where the correlation length becomes infinitely big. So you find the criticality by, it's still a long ways, but this tells you the fact that you can, the StatMech problem and a quantum problem are related in different spatial. That is what this story is all about. So, and next time, I mean, what we will do is look at this issue a little more. that at least the first that what if I started with a this is for the Ising model, that what would be the analog of we did the Ising model. The two paradigms that we have talked about are the Ising type, and the other is the Ginzburg-Landau type, right? So there is the Ising and the Ginzburg-Landau. That what if I started with the Ginzburg-Landau, then what would be the analog over here? So one needs to discuss that for a bit, and then so I'll do that and then go to the 2D Ising and show you the analog of the RG which we did for 1D and how it runs into some typical execution problems that these RGs have. When you are trying to do it on a lattice, execution is quite difficult, and so it's good to see that 1D seemed nice and simple, and you could get an answer how the 2D runs into trouble, and that so that we are after the this mid semester break, we can actually go ahead and do the how does one handle the Ginzburg-Landau and do perturbation theory and so on and so forth, which essentially is doing 5/4 theory in classical setting. All right.